Thank you very much for the invitation to be here. And so I'm not an expert on random matrices, but I'm looking forward to getting feedback on some work that I just did. And this is joint work with Souvik Dhara and Debankur Mukherjee, who was a postdoc with mine, and Souvik is a postdoc at MIT and Microsoft. But Debankur has now moved to Georgia Tech, so, okay. So the main object of interest here is if you look at an n by n symmetric matrix and you consider the R to P operator norm, which is defined, so it's the induced matrix norm, given the norms on the vector space, which is then you want to look, so the LP to LR, and you want to look the soup over all where the LR norm is less than or equal to 1 of the matrix applied to that vector, the LP norm of that matrix. So of course, why should one be interested in such objects? So of course, when R is equal to P equals 2, this is the classical case, and this just represents the largest singular value of A by the Courant-Fuchs-Weil min-max theorem. But in other cases, when P is equal to R, I'm always looking at the case when they're greater than 1 at this point, this arises in the study of some matrix condition estimates. For non-negative A, which is going to be the focus of this talk, it also arises in some oblivious routing problems. And of course, if you think of A as an adjacency matrix of a graph, then again, it's a non-negative matrix, and you'd be interested. Sometimes that's just denoted by just P with some abuse of notation. Okay, so another very special case of interest is what's called the Grothendieck LR problem. It's usually called the LP problem, but in our setting, it's better to call it the LR problem. So, which is just, what do you want to look? You want to look at this, maximizing this quadratic form, subject to a constraint on the LR norm of the random vector. Okay, so it's just a maximization of quadratic forms. And why are you interested? Again, of course, the R equals 2 case is the largest eigenvalue, but it's also the spectral partitioning or singular eigenvalue. And the other thing, the R is equal to infinity case, is something that was been related by Charik and Wirth to what's called correlation clustering. So if you have let's say particles, and you assign to each a value which says that either that to every pair you assign a value saying that they agree or they disagree or you're neutral, okay? And then you try to find clusters in which you will maximize the number of agreements within clusters and minimize across. So the correlation is defined as the number of agreements minus the number of disagreements, okay? Now if you want something that you want to maximize, then it turns out that that maximum correlation is indeed this value for R equals infinity. So in other words, both these norms arise in some kind of clustering problems. And so you can think of the intermediate between 2 and infinity can be viewed as a smooth interpolation. But it's also just an interesting question on its own, okay? And of course, this is also related to finding ground states in statistical physics, but of course, if A is non-negative, it won't be a spin glass, it'll just be, ferromagnetic. Okay, so what has this got to do with this, right? I mean, they're two different problems. This is the Grothendieck LR problem, and I could work it out on the board and show you that, in fact, so this is the original problem, and this is Grothendieck, that if you take P to be R star, which is the Holder conjugate of R, R minus 1 over R, then if A is non-negative and irreducible, then you can actually show that the R to R star norm is exactly MRA. Okay, so this is, there have been a lot of results studying whether this MRA is approximable or NP-hard. There are all these computational complexity questions that have been looked at by several people, including Naur, Schechtman, Guy, there's several other people. And also there's a work of Bhaskara and Vijay Raghavan about complexity issues in terms of solving this problem, both this problem as well as the R2P norm problem. So what is known is that in general, it's NP hard for general matrices A, but when A is non-negative, there is an algorithm for solving it, and I will tell you. But there are many other inapproximability results that are known that I can tell you later if you want. But right now I want to focus on the random case, and I'll try to make up for some lost time. But yes, Ofer.
Just a clarification, non-negative meaning entries?
Yes, entries, not positive, definitely. Entries, yeah. Throughout when I say non-negative, it'll be entries. I make that clear at some point. So, of course, if we want to try to understand, I thought, we can review sort of what is known in the case of the most studied case, which is when R equals P equals 2. Okay, so here, this is just a symmetric matrix, and for simplicity, I'm just going to take 0 diagonal. You can choose something else on the diagonal, it won't make any difference. But okay, so there's a celebrated result of Furedi and Komlosh, which says that if these are IID random variables, I mean subject to the symmetry condition, and that have bounded support, positive mean, and non-degenerate variance, and let lambda 1 be the largest eigenvalue, then they showed that as n tends to infinity, so of course, if I have the diagonal 0, then the mean is sort of n minus 1 mu. So if you subtract that, it actually goes to a normal random variable, okay? Converges to a normal random variable, which has a mean and some variance, so explicit variance given, okay? Okay, so some remarks about this. I mean, you think of this as some sort of fluctuation theorem, but the strange thing, if you haven't seen this before, of course, if you're a random matrix expert, it will not be surprising perhaps, but what is surprising here is that the fluctuation, once you take off the mean, usually you do have to do some additional scaling in order to get a CLT, right? But here, what you have is, firstly, you would expect maybe you do not have any further sort of mean coming up. But here the first thing is you have, one, a positive mean, and two, you have the fluctuations are really of order 1 around an order n quantity. Right, which can be thought of as what is called a rigidity phenomenon, that somehow that they are more concentrated than you would expect if you had sums of IID random variables, for instance, right? But this is the largest eigenvalue. It's behaving like its mean, but it's something that is much more concentrated than you would expect. Okay. Any questions? Okay. And if you contrast, of course, with the case when mu is equal to 0, of course, under some additional moment conditions, but let's say if you have mu equals 0 on Gaussian, so for instance, where there's, of course, a rescaling in terms of n to the 1 over 6, and then this will converge to a Tracy-Widom. And this is also, of course, different in that case, right? So the point is that all you've done is just shifted the mean to be positive. Since it's bounded support, this is really almost equivalent to saying non-negative entries, okay, since you're having bounded support. So you can think of this as being a result of our non-negative entries, but if you just, shift it back to, if you have a sort of centered, it has a very, very different feel to it. So in a very different qualitative result. It's not just quantitatively different. Okay, so we're interested in this, we can think of this as sort of a rank 1 perturbation because you're shifting all the means positive, and then you get this Gaussian behavior rather than the Tracy-Widom behavior. Okay, so how did they prove this result? So the basic idea is to first say that, okay, you have this homogeneous situation. If you look at the mean matrix, right, then 1, 1, 1 will be an eigenvalue for the mean matrix. And so the idea is to try to think that maybe 1 is nearly an eigenvalue corresponding to the largest, eigenvector corresponding to the largest eigenvalue. Okay. And then, of course, we know that in the spectral case, there are many algorithms that allow you to compute the largest eigenvalue. And one that's well known is what's called the von Mises iteration or the power method. Power iteration, power method, von Mises. And To obtain a good error, so you might start with this initial condition and then iterate using the power, and somehow want to try to prove that with a few iterations, you'll get close to the largest eigenvalue. Why would that help? The point is that this 1, 1, 1 vector is quite nice, and the power iteration is not a very complicated iteration. So that would be a much more tractable object than the original largest eigenvalue, for which you have no sort of explicit expression. And now you look at that other tractable object and you prove the central limit theorem for that. And if you have a close enough approximation, you can transfer that to the largest eigenvalue. Okay? So the idea is that you sort of establish asymptotic normality of the sequence of approximations or iterates thus obtained. So that is, you choose a certain iterate and then the sequence is with respect to n, of course. And it turns out that the second iterate of this power method, so the first iterate is actually just the sum, row sums. Okay, the ith value is the ith row sum. And here, these are the row sums that I'm just of the ANI. And the second iterate turns out to be this sum of the square of the row over the sum of the row sums themselves. So if you look at this, I mean, these are all in terms of IID. So of course it's nonlinear, but it's not really too bad at all, you know. So you can easily think how you could prove a central limit theorem for this object, which is not hard. And so that was the idea of Komloshin-Furedi. Of course, that's the basic idea. There are a lot of issues. Okay, is that clear? Okay, and then they also show that the largest eigenvalue is a great deal larger than the others. So of course, if you think that both in the when mu is positive, that is if you just have regular entries with no restrictions and you have non-negative entries, either way, you know that the empirical measure, the Wigner's law holds, which means that the empirical measure of the eigenvalues converges to a semicircular law, right? And in the case when you have a centered entries, then all the eigenvalues, it's not just max I greater than or equal to 1, all are sort of within this semicircular law, right? Which is small fluctuation around that. But you see the semicircular law is only saying something about the empirical measure, so it will allow little o of n eigenvalues potentially to be outside the support of the semicircular law, right? Little o of n, because you're dividing by n and then taking the limit. But in fact, even in the case of this, when you take the mu to be positive, even though the largest eigenvalue does go outside this support, all the others remain within this, and the sort of the support of this semicircular is like 2 sigma root n. Okay, so that's what this is saying. That clear? Because when you divide by n, you get. Okay, is that clear? Because this n to the 1/3 is of lower order than root n. Okay. So this observation was made earlier by Juhas in 81, but Komlosh made this more quantitative and precise, Komloshin-Furedi. Okay, so our focus, as I said, is going to be on the operator norm, and we would like to see if one can establish similar results. So it's asymptotic normality, and also try to understand L-infinity approximations for the maximizing vector, because these maximizing vectors turn out to be very important in these clustering problems, but also just in general, one wants to understand the maximizing vector and the asymptotic behavior. Now, in the case of the P equals R equals 2 case, you have the advantage that you have spectral methods working for you, right? But the minute you go away from that, you do not have spectral methods, so you would really have to do sort of revisit the ideas and try to see what you can do in this context. So let me first tell you sort of the first result, and then I'll tell you what we do in terms of the proof. So again, I said a symmetric matrix with 0 diagonal and non-negative entries. So the distribution of Fn should be on the positive. So, okay, I have maybe forgot to write that. And then you have bounds on the mean and the variance. Certain bounds, so don't worry too much about it. You could have kept all the means to be the same, then this would be satisfied, right, if all the means and all the variances are the same. But we allow this to have some dependence, and it'll make sense later. So I allow varying means, and I'll tell you why in a moment. And then some moment bounds on the distribution. So you remember that Komlosz-Furedi actually wanted bounded support, but we're allowing infinite support, but we do need some control of the moments. Okay, so there's some moment bounds that are needed. And so examples that satisfy assumption one, which will tell you why. So you look at the Erdős-Renyi graph with n and then mean mu n. So the point is that we're not only just looking at the case of GNP, for instance, the Erdős-Renyi, the dense graph, but we allow a certain sparsity, but it cannot be too sparse. Okay, so we allow some sparse graphs, but you can't go to 0 too fast. Okay. And here's another example of some classes of random variables that will satisfy these conditions. Okay, so you can always think, of course, of the mu n's just being constant and sigma n's, and that will also work. Okay, and so what is the first set of results is that you have, in addition to assumption one, I have another little condition on the sigma n's and mu n's. Again, if they're constant, they're trivially hold. Then as n tends to infinity, and they continue to hold in those examples that I mentioned. So now I'm going to define here a rescaled version of the norm so that it's sort of order one. Okay, so why is that? Because if you look at the p norm, right, it's natural to scale it by n to the minus 1 over p. Right, and the R norm you scale by R. So this is a natural quantity that arises because of the P norm and R norm, because remember each value in X, if the sum of X to the P is going to be 1, then you have each of them as sort of order 1 over P. So this is just to boost it to make a sort of order 1 quantity. Okay, so this is a natural scaling in this context. And what we want to study is this scaling. I mean, I'm going to look at the scaled version of this norm. So this should actually be A bar n, yeah. So what we have is if you center the A bar n by a suitable constant, then, and you divide by this variance, and that goes to a normal random variable, 0, 2. Okay. So okay. So even in the case P equals R equals 2, this sort of does some minor generalizations of Furedi's result and Komlosz-Furedi's result, which is in particular, it allows unbounded support and it allows sparse cases. Okay, okay. But in general, the asymptotic variance here, I think one thing to notice here is just 2, and it has no dependence on P or R beyond the fact that, of course, we did the scaling at the start. So the asymptotic variance doesn't depend on anything else other than this sort of order 1 term. It's just 2. It's sort of universal once you do the scaled operator norm, which is not obvious that that would be the case at all. Okay. Okay. So what's something about the outline of the proof? So again, here you might try to say, I want to look at the maximizing vector, okay, which is like the analog of the largest eigenvector, right? So this is the maximizing vector. And you want to find a good approximation in the L infinity norm, it turns out. That's the one that turns out to be relevant to this maximizing vector, okay? So a scaled version of 1 over n turns out to be close to the maximizer. Okay, and how do we show that? So again, because you have everything homogeneous, the expected value. So is again, so when P is less than R, this holds, it turns out, whenever the row sums are approximately the same. So in this step, we actually prove this for various deterministic sequences of random matrices that satisfy certain properties, and then show that certain random matrices have that property almost surely, sequences, okay? So what is, when P, it turns out actually when P is less than R, this is actually easier to prove than the P equals R case, okay? So when P is less than R, you can show that this holds whenever the row sums are approximately the same, and in fact this holds for any determined sequence of vertices that are what are called epsilon mu regular. And what I mean by that, you can think of this, it's good to think just as if AN is the adjacency matrix of a random graph, then the DNI is like the out degree of the vertex I. And we're saying that it's very close to n mu for all of them, right? So it's a regularity condition on this, which is why we call it epsilon mu regular, okay? And where, this row sum would just be, right, the out degree if you had a graph, directed graph. Okay, but otherwise it would be some edge weights that you're actually computing. And if you look at that, but when p equals r, so it turns out that we show that for certain sequences, which I will write down precisely, if it's the epsilon n mu n regular, then with epsilon n going to 0 and mu n being as before, then indeed you do have this 1n is adequately close to this, and I'll make that precise shortly. Okay, this is just giving you the outline first. Okay. But when p equals r, this turns out to be much more complicated. So it's not enough. You do need epsilon and mu n regularity, but you need an additional condition, which is what we call a well-balanced condition. And so what you need is you need some epsilon n going to 0 so that each an is epsilon n mu n regular. And also there exists some delta n, which is much smaller than mu n epsilon n, such that an is balanced in this way. So what does that mean? So what does it mean for something to be well-balanced? Maybe you can read the intuitively first. Intuitively, what it means is when an is an adjacency matrix, is that given any vertex subset of n, then most vertices have homogeneous connections with V. There are approximately mu times the size of V connections to V from most other vertices. Okay? So this is just some well-balanced condition, but this is satisfied by the random graph sequences that I mentioned. Okay, so then in this case, what is the precise bound that we get on the maximum eigenvector? So again, this will be trivially holding if all of these are constant. Then for one, and even if you have any sort of Erdős-Rényi, right, because mu n is equal to sigma n squared in that case. Okay, so then for one, for all the range, you have this sort of a bound, so that this is close to n to the minus 1 over r in a way that's actually decaying in a very precise way. Okay, where this constant that depends on p and r, as you see, it's p over r minus p when p is not equal to r. And so it's actually blowing up as p goes to r. It might be the artifact of our proof, I'm not sure, but the point is that we needed to do something different and we had to have this other well-balanced condition in order to get it for CRR, and it's not done by just taking this r to p, which you can't because it blows up. So you need something else and you need some other control. Okay, but you anyway have bounds like this. Okay, so what did we do? We said that even though we just have operator norms, we can show that the maximizing vector is close to a scaled version of the 1, 1, 1 direction. Okay? Okay. But, so what do we do with that then, with the step? So you might now use that maximizing eigenvector to get an approximation for the actual norm. But of course, if you have the value that is maximum, then you would just apply it, right, to get the norm. But now you have an approximation, so you might say, okay, Vn is approximately this, so maybe I should just approximate this by an to the n minus 1 over r, right? Find its norm, and that would give me an approximation. Okay, and then I try to do a CLT for this, right? Unfortunately, this approximation is insufficient at a CLT scale. Okay, so this is not a good idea. So what we did in the Komlers-Furedi, you started with one, you used the power iteration. You started with one, and you used the power iteration to get closer to your actual, to get a better approximation to the maximizing, the largest eigenvalue or the maximizing. And then you looked at that. But so here, what can we do? Instead, it turns out that for non-negative matrices, as I said, remember there were these issues of approximability and inapproximability of these norms. When things are non-negative, in fact, there is a nonlinear version of the power method due to Boyd back in 1974. And so what we're going to do is use that nonlinear version and start that iteration from Vn0, from this original guess, and then iterate, okay? Okay, just to tell you a little bit about Boyd's algorithm, if you're not familiar with it already. The basic idea is, of course, if we're looking at these norms, then what you're trying to, for some fixed matrix, now there's no an, I'm removing the an here. So you're looking at this functional, and you're trying to do a maximum, right, of that functional for x not equal to 0. Then you just want to find do some sort of gradient descent, right? Or you want to find the critical points of this, and then you could always reformulate it in terms of a fixed point problem. So that's precisely the details of the calculations are not as important, but as to see that it becomes quite nonlinear quite fast, right? So, which is not surprising, but the basic idea of Boyd's algorithm is you take this f of x, you find their critical points, set them equal to 0, so you can write this in this sort of this way using these operators, which are convenient, okay? So it's just doing a partial derivative of this thing that we're trying to maximize. You want to set them to be 0. You do some manipulations. If you equate the partial derivatives to 0, you get this in terms of these norms. You do a little more work, and you get this operator. Okay, so with phi over here, you get this normalized operator is exactly a fixed point. Okay, so the details are not too important, but what you do is you just find the critical points of this function that you're trying to find the maximum of, rewrite it as a fixed point equation, and then Boyd's algorithm is simply an iteration for the map W. Okay.
So this requires non-negativity?
Yes. So it requires non-negativity for it to converge to the global maximum. Otherwise, it converges to a critical point. That's where you use it. Thanks. Okay. Okay, but we actually need a rate of convergence because, remember, we are trying to start with this n to the minus 1 over r 1n and then converge. If it goes very slowly, then we'll have to do too many nonlinear iterations, which might be as complicated. We want as simple an object as possible to get a CLT4, right? So we needed to get rates of convergence. Boyd had some sort of very rough rates of convergence. But it turns out that what a key step in doing this is you define this linear transformation and this inner product around, so you sort of transform this S nu. I'll just remind you that S, the normalized version of S was this iterative map, okay? So rather than look at the normalized version, I can just take S, I want to linearize it. So I linearize it at the maximum, okay? So I have this V, which of course we don't know what it is, but you're going to linearize it in the following way. And again, these are all just sort of algebraic manipulations. But if you linearize this map at the point V, then, which was the maximum, remember, then you get this B, which is now linear. And you define this inner product, which depends on this nu. And you have this, it generates a V norm, okay? So with respect to the maximum, you define a new norm. And it turns out that this operator B is symmetric and positive definite with respect to this above inner product. Okay, this inner product that you define. And then you now look at the Rayleigh, B is symmetric and positive implies that the eigenspace of B has, n orthonormal bases, vectors. And you look at n critical values of the Rayleigh coefficient. The Rayleigh coefficient being defined in this way, which you can write down explicitly in terms of your original A. Okay, so that's just a fact for any positive symmetric definite matrix. Okay. And one can also show, remember, gamma P was the critical value that you had. So you can show that B nu, so it's actually an eigenvalue for this. Okay, gamma P is gamma to the P, which is this value that we want, which is the value the maximum value, right? So, okay, but you also have these other critical values, lambda 2, lambda 3, lambda n, because they're n eigenvalues. And using that and using a lot of manipulations, we actually get quantitative rates of convergence for Boyd's algorithm. The main thing that for the nonlinear power method, which is of this form. So xk plus 1 is just the k plus 1th iterate after you started with n to the minus 1 over r1, right? So that's I applied the map W, k plus 1 times, and I look at its difference from the original the actual maximizing vector, in the V norm, right? So I look at the V norm distance between this and this, and I can bound that in terms of course, the previous iterate's distance. And what comes up here is interesting. If you had the regular power method, for those who know, it's an iteration, you of course get, the rate of convergence is governed by the ratio of the second eigenvalue to the first eigenvalue, right? And here what you get is the ratio of these critical values of the Rayleigh coefficient, okay, in the nonlinear setting. So you have this parallel, okay. So continuing now that we have some rates of convergence, our ansatz is that we just do one step of Boyd's nonlinear power iteration and see if that provides. Of course, remember, Komlosj-Furedi had to do 2 steps of the power method before they got, but we were hoping one step would be enough because, as you see, with one step, I'll show you what one step looks like, okay? Not too exciting, right? Like you don't want to deal with that, but okay, so we have this sort of very nonlinear object, which is what you get after one step. And again, we show that this is well approximated, and as in step 1, we show this for deterministic sequence and then verified for random matrices. So once we have this, we want to show that after one step, it is close enough, which is an estimate that we get. And then we want to prove asymptotic normality of this, right? Okay. But now this is it's not like the sum of some IID divided by this, square divided by the sum of the thing. It's so highly nonlinear. But of course, you could try to do nonlinear CLT, apply methods that nonlinear functionals, right, of IID random variables. But unfortunately, the standard, approaches to doing CLTs for nonlinear functions do not apply directly. So we had to actually resort to a sort of Taylor expansion approach. And roughly speaking, very roughly speaking, we can show that this ANR to the P has this factor, and where you do get some things that are related to the sums. Okay, but this is a very rough. You have to do a lot of work to actually show something like this. Okay? So how am I getting this? I'm first approximating this by this, right? Because it was the one iteration of this nonlinear power method, right? And we knew rates of convergence because we had, so let me just go back. Actually, I don't know if I made this clear. So remember that you had this iteration, right? And we knew the distance of n to the minus 1r n from V, and we said it was not good enough. But after you do this, you get one closer, and that's good enough for a CLT bound. So what we really want to show is this satisfies the CLT, and so we're showing that this thing is approximable by something like this. Okay, and then you sort of do some appropriate centering and scaling to obtain the desired CLT result. Okay. Okay. Any questions? Yes. So we first get bounds on the distance between. Remember, we had the distance between the n minus 1 over r to the 1, which was for deterministic matrices, and the maximizing vector. But then when I iterate, I had this rates of convergence. So I get a better convergence. So what I mean, you mean what lets me know that it's enough? So it's like if you know it's order, for suppose if it was an ordinary CLT, then if you know it's of order n to the little o of n to the half, you're done. So you just have to show that it's little o of 1 over here, which you can do. Yes, yes, exactly. Okay, so that's, which is right. How do we prove this? So this, yes, thank you for that question. So you need to get bounds on this, right? So how, your question really bounds on, so what governs this rate of convergence is you have to understand the ratio of this lambda 2 to this gamma p. And just as in the case of Komlosj-Furedi, this lambda 2 is indeed very small. How do you show that? That requires, we used results of Antti Knowles and three papers, some of them just came out in the last 2 years, on actually what is the second eigenvalue of some random matrices. So the second largest eigenvalue, the spectral distribution of, so you need to actually study that in order to understand, to get bounds on this lambda 2. So we needed to prove that that holds for these random matrices. In fact, we showed it for deterministic sequences and showed the random matrices satisfied. Okay, so that was a key step in being able to show the convergence, that it's close enough. Is that, thanks for the question, yeah. Okay. Okay, so that was as far as the homogeneous setting goes, but we were interested in also seeing to what extent do you need IID entries in the random matrix? Can you actually go away from that and do inhomogeneous? So you still assume independent entries at this point, and you have, again, means, and then you have some more bounds on this. Again, if they're all not n-dependent, these bounds can be ignored. These bounds on the means and the variances are only if you want them to allow to change with n. Okay. And so then we show that a similar result holds. And it's, again, you have some condition on the sparsity if you think of these as adjacency matrices of graphs. And then again, we get just instead of, we had, remember before you had n over sigma over here. I mean, you had 1 over sigma, so here you have this sort of different scaling. But again, you get the same normal 0, 2. Here. We had written it slightly differently here with the sigma squared over mu and 2 sigma. But now I've taken that sigma this way because it's n-dependent. Okay? And again, you get this p minus 1 over plus 1 over r minus 1, and then there's some term here. Again, it's more general because you have this sigmas which could depend on n. Is that clear? So in fact, for these, even both in this case and the previous case, even the centering was not, completely obvious. But of course, you can take the expected value and try to guess what it is. But the centering is also something that we show. Okay, and you can get similar results on the eigenvalues. This is just more complicated because it's much harder to get bounds on the second eigenvalue. It's harder to show all these results, these concentration results. So it turns out the concentration results that we need are, for instance, the row sums should have some nice, which is for the well-balanced property. So when it's inhomogeneous, you have to do more work to do that. And then you have to show that they're also well-balanced. That's much more hard work when you have this inhomogeneous setting, but the basic idea is similar. So actually we had finished everything. We were about to send out the homogeneous paper when we saw this other recent result, which we thought of Art Knowles and one other person, for which just came out last year, towards the end of last year, which we thought we could use in order to actually prove bounds on the second largest eigenvalue. So we said we can actually extend this to the inhomogeneous setting. So we did some more work and generalized this. Okay, and again, you get the same sort of bounds except with k replaced by k1, where k1 is this sigma bar n squared instead of sigma n squared. Okay, so you get these bounds, and then you do everything else in a similar way. Okay, so to summarize, we've studied sort of the asymptotics of R to P operator norms when 1 is less than or equal to P is less than R less than infinity. So you might ask, why did we not allow P equals to 1 or I equals infinity? That just turns out to be a trivial case. So it's not because it's hard, but because it's trivial. But we do insist that P is less than R in this case, okay? So you might ask why, and I will tell you in a minute. But the natural generalization of the largest eigenvalue problem, spectral methods don't apply, but there seem to be some analogs that seem to be interesting. But there are many questions that remain. So you could study more general inhomogeneities. For instance, a recent result in November of last year by Arijit Chakraborty, Sukrit Chakraborty, Rajat looked at sort of inhomogeneous Erdős-Rényi random graphs. So this is not for operator norms. This is just for the R equals P equals 2 case, right? They're looking at the eigenvalues, again, outside the bulk, but of inhomogeneous, like coming from a random graph that's like generated a weighted random graph, if you know what that is. So you have a certain function, and the probability that you connect is proportional to Wi, Wj over that function. So there are different ways of doing inhomogeneous random graphs. So they chose one such inhomogeneous random graph model, and they studied the eigenvalues. And it's more complicated because these are, when you don't have sort of just rank 1 perturbations of a centered matrix, then the analysis becomes much more complicated. And so they have some nice work. So you could also study these things in the context of operator norms. And then there's a hypercontractive case when R is less than P. Okay. In this case, one of the issues is that the maximum, so in this case, which I didn't tell you, when P is less than R, you know that the maximum is uniquely attained. So it's not that I found a maximal V, but there is a unique maximum. In this case, there could be multiple maxima. So that's just one manifestation of why this is hard, and I don't think even many approximability results are understood in this setting, whereas there's a lot understood in the P less than R setting. And then this is ongoing work that we're looking at. We've made the study of operator norms for the centered random matrices. So if you've just had IID Gaussian, can you understand what the centered norm is, right? And that turns out to be much more difficult. But we have some ideas on at least what is the right scaling in that case. Okay, thank you.